Okay, so we have class today. We have class on Wednesday, not by my choosing, but I can't cancel class on Wednesday. So there's few things we get in trouble for here, but that would be one of them. So I will have class here. If you have to travel and you can't be here or something like that, just send me an email, let me know. I will record the lecture. If I'm the only one here, I'm not going to record a lecture, all right? All right. I'm not encouraging you to miss. I'm just saying that I do plan on putting the lecture up unless I have 0 attendance. All right. I just wanted to kind of recap the important things that we're going to need today to continue what we were doing last time. So just remember that if you're given a vector field, this is a 2-dimensional vector field, but this also works with 3-dimensional. If you have a 2-dimensional vector field, that this line integral over C, along C over the vector field F with respect to the vector R is going to be our work integral. Right? Does that look familiar? Okay. Now, you can also rewrite this integral as the line integral over the curve C of P, which is just the scalar function, the x component of the vector field, with respect to x, plus the y component of the vector field, which is another scalar function with respect to y. This is just notation. We just need to be comfortable with it. And this is the big thing. If, I'm sorry, I'm getting over something right now. If the vector field f is equal to the gradient of some scalar function little f, that means, what does that mean if that's true? We would say that this capital F is what? Conservative. So if f is a conservative vector field, and the curve C that you're integrating over can be parametrized with the vector function r of t, where t is restricted between a and b, then this work integral basically turns out to be the difference of the two endpoints. This is the fundamental theorem of line integrals from last class. So you have to basically find out what are the two endpoints of this curve, take those two endpoints, and plug them into this scalar function, little f, which would either have to be provided to you or you would have to actually recover that yourself. So, okay. Now, that's just a reminder. Let's get back to where we left off. So I've gone through the fundamental theorem of line integrals, which is exactly what I just had down here. Okay. And then we stopped because this theorem that we got right here is connected to the fundamental theorem of line integrals, but not in a way that we would hope it is. So let's just read what this what this theorem says. If you have a closed curve, right, starts at a point, goes around, ends at the same point, right? That's the definition of a closed curve. Then let's look at what this theorem says. Here's the theorem. It says the work, I'm just going to keep calling this the work integral just because I want you to remember it as the work integral. Just keep in mind that it's not always calculating work, all right? If it's force in directed distance, then it's work, but it could be other things. But it's just easier for me to refer to it that way. So the work integral is path independent in D. So this is a definition, actually. We are defining what it means to be path independent. To be path independent in some domain D, here's what would have to happen. The line integral, or the work integral, would have to be equal to 0 for every closed curve or path in D. So let me try and explain what's happening here. We have some domain. Let's just call this D, and we're going to make it 2-dimensional. And then we have a vector field in there, right? And the vector field is a bunch of little vectors all over the place, right? Like we could draw them. They might be doing different things, right? So we have some vector field in here, F. Then we have some curve in here, C. And it's a closed curve, right? So I start here, I go somewhere, I come back. All right. If I do the work integral over this curve C, and get 0, can I say that this is path independent? No. What would I have to do? Every curve, every closed curve, right? That means I'd have to be able to go and take any closed curve I could ever come up with. Sorry, I messed that one up. I cut back on itself. I'm not supposed to do that. All right, so every possible closed curve in this domain D, if the work is 0 on every one of them, then we can say it's path independent. Well, that sucks because I can't check every single one of them, can I? Right? So although the theorem is good, it really is impossible for us to check every single one. However, if the vector field F, if this F is conservative, right? If F is the gradient of little f, what do we know from the fundamental theorem of line integrals? That the work is equal to the difference of the scalar function at the endpoints, right? Yes? Yes. And therefore, if I start at any closed curve, right? I go and I draw a curve and come back to that same point, what's work going to be there? It's going to be 0, right? And that would work for any closed curve because I'm going to start somewhere and come back to the same point. So although this theorem doesn't appear to be useful because it requires that we check every single curve, if the vector field is conservative, then we know that the work is 0, and then we can say that it is path independent. Understand? So in general, over just a general vector field, it's difficult to show path independence. But over conservative vector fields, you have path independence. Got it? Okay. That's what it says on the very bottom. So line integrals on closed paths of conservative vector fields are path independent. All right, we need a couple of other things before we move on. Oh, wow. It's that infamous red marker. It works really good, doesn't erase well. Oh my goodness.
Those aren't permanent?
They are not permanent. I've come across a few of those this semester where they just really, they love to write, but they hate to erase. All right. Yep, it's usually red. So how do we determine if F is a conservative vector field, right? Now, that means if someone gives us a vector field, can we actually figure out whether or not it's conservative? And the way we tried doing it once, right? Do you remember us trying to go backwards and integrate to try and find out like the little f, if I gave you the capital F? Well, there's a theorem, all right, that makes this very, very easy to do. Very easy. If we're talking about two-dimensional vector fields. And go ahead.
Does one work for three-dimensional?
There is something for three-dimensional, but we're not ready for it yet. Yes. So there it is right there. So let's say that you are given a vector field where you have two scalar functions, p and q, right? The two component functions of your vector field. Then we have to make sure that our vector field is on a simply connected region in D. So that's why I looked up here and I said, this theorem works as long as the region you're talking about is simply connected. This is a simply connected region. This is not a simply connected region. Can you tell the big difference between those two? Is it obvious? There's a hole? Yeah. I mean, basically, here's a more technical way of thinking about it. If I go into this region and I draw a closed loop, can I shrink everything down to a single point? Like imagine that's a rubber band. Can I shrink everything down to one point and not leave the region? Compare that to like if I took this and I went and drew that around there. Every single point on that blue curve is in the region, isn't it? But if I try and shrink that down, I'm going to get stuck, right? This hole is going to stop me from shrinking it. And so to get back to a single point, I'm going to have to cut through the hole, and that's not a simply connected region, all right? Okay. So this theorem holds as long as you're on a simply connected region. And it says that you need to take the partial derivative of the p function with respect to y and the partial derivative of the q function with respect to x and see if they're equal to each other. It's a super simple check. If that's true, then it's a conservative vector field. Now, not here to prove the theorem, just provide it for us, all right? So let's just check to see if this is a conservative vector field or not. So this right here is our p, our scalar function p, and here's our scalar function q. So p is a function of x and y, q is a function of x and y, right? They both are functions of x and y. So what I need to check right now is the partial of p with respect to y equal to the partial of q with respect to x? Is that true? So what is the partial of p with respect to y? 2x. Is that equal to partial of q with respect to x? Yes. Check. What does that mean? It's conservative. That's pretty straightforward, isn't it? Isn't that a nice little theorem? I think so. It's a simple way to check whether or not you have a conservative vector field or not. Okay, now that we know it's a conservative vector field, we know that there must be a little scalar function, little f, right? That if you take the gradient of that little f, you should get that vector field. So how do we actually go find the little f now? So this is just asking you to remember that if f is conservative, then there exists a scalar function such that the gradient of little f is the capital F. In such case, little f is called the potential function for the vector field f. We now learn how to find potential functions if it exists, because you don't always have potential functions. If it's not conservative, you don't have a potential function. But if the potential function exists, in other words, it is conservative, then we will use this technique called partial integration. So we're going to do it right now. We're going to do it for this one right here. This is a different problem. So first of all, is this conservative? So let's check. What is the partial of p with respect to y? Is that equal to the partial of q with respect to x? So partial of p with respect to y, this is p. Q is just x squared, right? So p 2x, and then this one is 2x again. Check. It's conservative, right? Therefore, there must be a little f that is the potential function, that when I take its gradient, I get this, right? So let's see if this rings a bell. Because we did try this on one problem earlier, about 2 weeks ago, I think, and we found that we couldn't come up with the little f. It didn't exist. But this one should. So here's what I know. This part right here, right? If capital F, that vector field, is the gradient of little f, which it is, right? Then what we're saying is that capital F is equal to the partial of little f with respect to x times partial of little f with respect to y. Because that's what the gradient of little f is, isn't it? Right? And that means that 1 plus 2xy plus natural log x, comma x squared is equal to partial of f with respect to x, partial of f with respect to y. I was wondering how it was going to be once I started talking today. All right. Understand what I'm doing here? Just setting up what it means to be conservative. That means this vector field is the gradient of some little f. Now what I can start doing is equating things. I know that this has to be equal to this, right? And that's what I'm going to start with. I'm going to start all of my work with that statement right there. So I think what I'll do is I'll come over here and write this down. I know that little f, partial with respect to x, must be 1 plus 2xy plus natural log x. I'm going to erase that because it's in my way. Do you remember what I did at this point? Integrate with respect to x, because I know that to get here, I had to take the derivative with respect to x, right? So to go backwards, I'm going to integrate with respect to x. So I'm going to take the antiderivative on the left side of this with respect to x. Then I'm going to integrate the left side with respect to x. And I'm going to erase that. I'll need that later, but I need room up here. All right, so now, what is the antiderivative of this with, well, this side? What's the antiderivative of this with respect to x? Little f, just little f. This should be my scalar function, right? Because this means the derivative of little f with respect to x. So the antiderivative of that would be just little f. Now the right side is the antiderivative of this with respect to x. So what's the antiderivative of 1 with respect to x? X. And then here you treat y like a constant. So what's the antiderivative of this right here? X squared. So we're going to have plus x squared y. And then here, the antiderivative of natural log x. Yeah, this is one from Cal 2. X ln x minus x. Not the derivative of natural log, the antiderivative. Does that look familiar? Okay, I think in my Cal 2 class, I let you all write that down on your formula sheets.
B and then B.
What's that?
Like B and then B. Minus.
Well, does anyone remember how to do that integration? Like, how do you integrate natural log x? You do integration by parts. And you let this be your u, right? And then you let 1 be your dv, and then you integrate and do your little thing, and it works out. So, okay, so we're okay with that? We're missing something, though. Plus a constant is what it normally is, right? But I also talked about this last time, that this could be more than a constant. It could actually be anything that has just y in it, right? Or a constant in it. Do you all agree? So I put here something like g of y, any function of y, which could include constants. So the way you think about it is, let's say that this piece right here was y squared, right? Let's say it was y squared. Then if I took the derivative of this with respect to x, to come back to this, I would take derivative of x and get 1, derivative of this, get 2xy. Derivative of all this would be natural log of x. And then what would the derivative of this be? 0, because it has y's in it only, right? But I have to account for that when I go backwards. So I have to put g of y here. Now, great. I know little f, don't I? Like, kind of. I know what little f needs to look like within a function of y. I just need to figure out what this function of y is, right? So now what I do is I take this result and I take its derivative with respect to y, and I figure out what I would get. And I'm going to try and match it to this, because that's what it needs to be, right? Okay, so what is the derivative of f with respect to y? So that's 0. This is x squared. All right, what's the derivative of all of this right here? 0. So I'm not going to put it. And then what's the derivative of g of y? Let's say g prime of y, right? Now, this means that q, right? Q is the partial of f with respect to y. This has to match with q. So I'm going to put here, but x squared plus g prime of y must equal x squared, which means that g prime of y must be 0, right? Just subtract x squared on both sides. And now, what were we trying to find? We weren't trying to find what g prime was. We were actually trying to find what g was, right? So what would g be? You integrate, right? You can integrate g prime y with respect to y and integrate 0 with respect to y. And I hope that's obvious that that means g of y must be a constant. The antiderivative of 0 is a constant. So let me write down the potential function. The potential function, the answer to this question, okay, is this, and then plus any constant I want. Okay, any constant I want. So you may have more than one potential function, right? You can have an infinite family of them, but they're all going to be like scalar multiples, or not scalar multiples, all shifts, vertical shifts of one another, just like antiderivatives have always been. It's a family. So I'm just going to put plus c. Did I do what? Huh? Oh, did I not cancel the x's out? I'm sorry. Yes, I should cancel those out. Okay? That's how you do it. That was pretty straightforward, I think. Especially because it turned out to be a constant. It's not always going to be that way. Okay, so now let's go to this problem. Let's act like we just walked into class and this is the problem that's on the board, all right? If f is this vector field, which is the one we were just working with, right? Find the work, right? Where c is given by this curve. So we could do the hard way, which would be to do this. We can make this the line integral from 1 to 2 of f evaluated at the curve dotted with the derivative of the curve with respect to t. That would be, 1 to 2. Okay, that would be the hard way to do this, because what you have to do is you have to take the derivative of this, you have to take this curve and plug it into this vector function, which means you replace all your x's with t squared plus 1, all your y's with t plus 2, and then you're going to dot those together, and then you're going to integrate those with respect to t. And that would be a lot of work, wouldn't it? But we realize that this vector field is conservative, right? So if we were faced with this problem, the first thing we would do is go, that looks like it would suck. It would take some time. Maybe I could do it. Who knows? But let me just check, is it conservative, right? So I would ask myself, is f conservative? And I turn out, yes, it is. Why? Because you would check those partials, right? Partial of p with respect to y equals partial of q with respect to x. It would check out. We did that in the previous example. So then what you would do is after you find out that f is conservative, you would find little f, which we just did, right? And little f was, what? I forgot already. I canceled the x, right? Yeah. So let's go x squared. It was x squared y plus x ln x. And that was it, right? Plus some constant, right? OK, so I'm going to use the constant 0. Because I can use any potential function I want. So I'm going to use the constant 0. So that's little f, right? Now, what?
Plug B.
What's that?
Plug 2 and then
Plug 2 into where?
into F.
Into this? What are you using? You're on the right track, but what are you using? I don't understand. Why aren't you doing this? Because the fundamental theorem of line integrals says that if this vector field is conservative, right, then all you have to do is evaluate the scalar function, little f, at the two endpoints of this curve, right? None of this work is required. So I need to find the two endpoints of the curve first. So r is sitting out here, right? This is our curve r. What? R, okay? Here and here are the two endpoints. There's some direction on this. I need to find this point. This is r of a, that's where we start. This is r of b. Understand? I need to find those 2 points. Once I find those 2 points, what do I do with them? Plug them into f, right? And subtract. So what I'm doing here to do this, I'm not doing this. I'm not going to do this. What I'm going to do is I'm going to take little scalar function f, and I'm going to evaluate it at r of b, and I'm going to subtract the scalar function f evaluated at r of a. And this is the fundamental theorem of line integrals. All right, that's what I'm using here. Fundamental theorem of line integrals to do this. So what is r of b? For us, that's really r of 2. And r of a is really r of 1. And that's all given to us, right? B and a.
Yeah, but you still have to turn the little f terms into terms of t, don't you?
Little f in terms of t?
Yeah, if you're plugging in the two inputs at f, you're not giving your x and y coordinates, and you still need to convert it for.
R is going to give me my x and y coordinates.
Well, what I'm saying is, don't you need to turn little f into t squared plus 1?
Uh-uh.
No?
No, you could, but it achieves the same result. Okay, because what I'm going to do instead, what was being suggested is, why don't we replace x with this and then y with that and then plug in the two endpoints? You could do that, but you get the same result if I just, let me plug 2 into this, right? Let's plug 2 into this. And what do you get? So what's r of 2? It's a vector, right? It's the vector 5, 4, right? What's r of 1? Right, that's what we're doing here. So this is 2, 3. Okay. So what I need to do now, and I'm gonna continue this, I'm gonna move it up here. What I need to do now is I need to take f right here and evaluate it at r of 2. And this is where I told you in the past, it's a little weird that you're plugging a vector into a scalar function. But what we mean is just plug in 5 for x and 4 for y. This is just notation, right? The meaning of it is just replace x with 5 and y with 4. Okay, minus f of the vector 2, 3. Okay? Now this is equal to, let's plug in right here. We have x squared y plus, so x squared would be 25 times 4, right? That's 100 plus 5 ln of y, which, or no, 5 ln of 5, like that. That's what I get when I plug in that point. And then minus, now we plug in 2, so 4 times 3, right? 12 plus 2, it's x, I don't know why I'm doing y. 2 ln 2. We can clean this up a little bit. This is 100 minus 12 plus 5 ln 5 minus 2 ln 2. I'm sorry I don't have your take-homes graded. My plan was to get them all graded and get them back to you. I started feeling bad last week. And on Friday, I was going to come in Friday and sit in my office and finish them out because I've got them about halfway graded. And then I started feeling bad, and I came to a meeting on Friday, and as soon as the meeting was over, I went home. And I realized at home that I didn't have the tests, that they were sitting on my desk. So I apologize. My plan is to get caught up tonight. We'll see. All right, what is this equal to? This is 88 plus ln 5 to the 5 over 2 to the 2. What the hell? All right, this is properties of exponent or logs. This 5 can come up as a power, this 2 can come up as a power, and then subtraction between two logs becomes a single log with division. This is most likely how the book would have it. They might even like figure out what those numbers are, I don't know. But okay, we good? That is the work. Okay, we have not seen what it takes to show that a vector field in R3 is conservative. Okay, so we don't have a quick check. Not yet. We will, okay? Not yet, though. But we can still ask ourselves the question, you know, is there a potential function for a three-dimensional vector field? So if I give you this vector field, notice that it is three-dimensional now, then can we find its potential function? So I'm telling you this is conservative, all right? So there is a little f. So I'm going to label these. This is going to be P, this is Q, and this is R. We know that this vector field should be equal to the gradient of f, which means that the vector field should be equal to partial of little f with respect to x, partial of little f with respect to y, partial of little f with respect to z. Why do we know that f is the gradient of little f? How do we know that? Huh? How do we know that this is conservative? Yeah, we are going to check this, right, to see, but how do we know that I can, like, how can I write this down? How do I know that this is true? We don't. It's because I'm telling you it is. This is important, okay? Because this, you have to understand we are stepping over that hurdle, okay? You're trusting me that this is conservative. If it is, then this is what would be true, right? Okay. Now, you would never want to do this if you don't know it's conservative, because you might be wasting a lot of time and energy. All right, so let's see. How about we do what we did earlier? We know if this is true, then we know that this one has to be the partial little f with respect to x. This one would have to be the partial of little f with respect to y, and that one would have to be the partial of little f with respect to z, right? That's what it would take. So let's start with that very first one. The partial of little f with respect to x must be 2xz. Now I know a lot of you are ready for plus y squared, are ready for turkey, and you understood the previous example. But there's something subtle in this one that I want to make sure everyone understands, and it's about to happen, okay? Right now, what do? Integrate with respect to x, right? So integrate this with respect to x, and then you integrate this entire side here with respect to x, right? That's all the same, no big deal, everything's good. The left side now becomes little f. And the right side, antiderivative of 2xz, x squared z. And then plus antiderivative of y squared with respect to x is xy squared. Plus G what? Zy. Why zy? Okay, so before, when we only had two-dimensional vector field, we were only playing with two variables, x and y. So when we did this constant integration, we said, hey, it could be more than a constant. It could actually have y's in it also. But now that we have y's and z's and x's, this part right here, this function g, could have y's or z's, right? And then the derivative of that would still be 0 with respect to x. So I'm going to put g of y comma z. It is an actual function of two variables, right?
Does that imply a function of a single variable might exist also?
It could be. It could be just y's. It could be just z's. It could be a constant. What I can't do is eliminate the possibility that there could be y's and z's mixed together, right? This right here could be some crazy function like z squared cosine y, right? It could. And if I took the derivative of this whole thing with respect to x, that would be 0. And it wouldn't appear here, wouldn't it? Right? It wouldn't appear here. But I have to account for that going backwards, that it could be some crazy function of y and z. All right, fine. So that's a major difference between this and the previous one, right? Now, what did we do at this point? We now took the derivative of this with respect to y and matched it up with this, right? So let's do that. What is the derivative of this with respect to y? And remember what we need. All we need right here, if we can figure out what that is, we're done, okay? If I can figure out what that is, we are done with the problem. So what is the partial of this with respect to y? 2xy. And what must that equal? Sorry, oops. You got to take derivative of this, y'all. It's the derivative of this with respect to y, which we write g subscript y. That's the partial of g with respect to y. You don't want to write g prime here because you don't know what variable you're differentiating with respect to. Understand? Derivative of this with respect to y is this. But what must this match? But 2xy plus g, partial of g with respect to y must equal 2xy. This is a really boring example. Which means the partial of g with respect to y must be 0, right? Subtract 2xy on both sides. Next step. Integrate this with respect to y. And that should give us back g again, shouldn't it? So when I take the integral of g, the derivative of g with respect to y, and I integrate that with respect to y, and then I integrate 0 with respect to y, I get what? C? Yeah, so look, this is a critical point. Here, this is just g, isn't it? Okay. Now, when we integrate this side, we're integrating with respect to y, right? We're integrating 0, which normally you would say this must be a constant. But what if it has z's in it? Right? What if this has z's in it? The derivative of that would be 0 with respect to y. But it could only have z's in it. It couldn't have any y's, and it couldn't have any x's. The reason it couldn't have any x's is because where did this all come from? We assumed that g was a function of y and z only. So I know that this side right here is some function h of z, possibly. Y'all with me? Okay. So what? Yeah, basically all I've been able to do now is take this line right here, and I've been able to say, hey, look, this f is x squared z plus xy squared plus g, which was some function of y and z. But in all my work, what I realize is that g, if it's anything, it has to only have z's in it. Okay? So now I'm at this point, h of z. So what can we do now? We have a third component we can work with, right?
So do you have to take the partial with respect to z?
Absolutely. Let's take the partial of this with respect to z. So we take the partial of this with respect to z, and you get, what? X squared. Partial of this with respect to z? 0 plus here. You could say h prime of z. Could you say h prime of z this time? Yes, because h is a function of a single variable. You could also write h subscript z. It's the same thing. Whatever you prefer. What do you want, prime or subscript? Prime? Okay. H prime is z. All right, so that's what I know about the partial of f with respect to z. Now, I need that to match what? This? But x squared plus h prime of z must equal x squared plus 3z squared, right? I'm trying to match it to the third component. Subtract x squared on both sides, and you get h prime of z must be 3z squared. Well, now you know what h is, right? You can just integrate now? Or, I mean, you could just look at that and tell what it came from, right? So what is h of z then? Z cubed plus some constant. Now, this time I can say it's a constant because h could only have z's in it. So the most this could be would be a constant after that. So I think we have it. Okay? Our final answer is that little f must be x squared z plus xy squared plus z cubed plus some constant. There it is. Bless you. Now, here's the good news. If you find a potential function, right, you can always check to see if it's right by just taking the gradient. If you take the gradient of this and you get back the vector field, then you've done it correctly, right? So if we just do the partial of this with respect to x, we should get that. Partial of this with respect to y, we should get that. Partial of this with respect to z, we should get that. Do you get an idea kind of how this partial integration works? I mean, you're going to have to practice a little bit, which is why I assign homework. The tricky part, I think, again, is keeping track of that antiderivative of 0 is not a constant in this case. It's a function of z only. Over here, when we had that g, that it was a function of possibly y and z.
So the process, I guess, think on this, because I remember going through this in differential.
Okay.
And I was able to go through the process, but I wasn't really understanding. It seems a little bit clearer. So you're returning back to the function, to this partial function, I guess, with like, you have f of x, partial x, right? When you're integrating, you're going back to this original function.
Yes.
And then from that function, once we have what our constant is, then we take its derivative.
Again, yes.
And then once that derivative is taken.
Integrate back again.
But then we're going back with the function with the new constant, which is in this case h of z.
Yeah.
And then we'll take its derivative again.
Yep.
Back.
Yep.
So that's just the process.
You're just you're basically if you want to look at it like here's what we do. We're starting. We know what little f of x is, right? We start with that. Okay. We integrate that. When we integrate that, we get f. But it's f, but we still don't know. There's still some other things in here, like a function of y and z. We still don't know a little bit about f, right? So then we say, okay, let's take the derivative of this f with respect to y. So we differentiate it, right?
Right.
So now we're at this, and we play a matching game. And then we integrate again. And now we have f plus now we've actually nailed down a little bit more information about it. And then we differentiate again, and then integrate, and then we finally get back to the f. So yes, it is this game of integrate, differentiate, back and forth until you can recover everything that you need.
So at some point in this class, are we going to get to the point where the functions are a little bit more complicated?
Oh yeah, your homework. Yeah, yeah. That's you need to do the homework so that you can, these were just like introductory problems. Now you go and you try and do the homework, and they get a little more challenging, and then,
So later on, are you going to explain why that z component makes the whole problem conservative?
Am I going to explain what?
Why that function is conservative, or that vector is conservative?
How am I going to explain why it is?
Why?
Like how we can check?
Yeah.
Yes, I'll show you the test for it.
Okay.
Yeah, but we need to define something first that we haven't defined.
Okay.
Okay, that's the homework for that section. Yes,
Said there was going to be a way for us to check if it was
conservative vector field.
for that? Like before we did the work.
Uh-huh.
Was there going to be a formula for us to check?
Yes.
Oh.
Okay, so let's just all be clear. If I give you a two-dimensional vector field right now, capital F, vector field equals PQ, we have a check to see if it's conservative. You take the partial of P with respect to Y, you see if it's equal to the partial of Q with respect to X. That's for two-dimensional. For a three-dimensional vector field, there is a test, but it's not that test, okay? You will get that test. I just can't give it to you yet. We need to define what the curl of a vector field is, and we haven't talked about the curl of a vector field. All right, that's the homework. It's a really nice test. I mean, it's just like that other one, really clean and easy to use. It's one of my favorite theorems. in this entire book. And the reason why is because, I don't know, I guess most of the theorems up to this point seem to, I don't know, these just seem to be two ideas that are so far from each other that the fact that we can bring them together into a theorem to me just seems kind of amazing. So let's just get right to it. Green's theorem. All right, so Green's theorem is a theorem that connects the line integral around a simple closed curve to the double integral over the region bounded by the curve. So in other words, if we have a region D, now when we first started doing double integrals, we had rectangular regions, then we did type 1 regions, type 2 regions, we did polar regions, right? We did all these types of regions, two-dimensional regions. So D here is a region. But if it's a closed bounded region, then there is a curve that encloses that region D, right? The outer edge. And if we take what's called the positive orientation of the simple closed curve C, then what we mean is counterclockwise traversal of the curve. So anytime you go counterclockwise around a curve, that's called positive orientation. Negative orientation would be the other way around, okay? Clockwise. So you give me a simple, you give me a bounded region, right? Even like this, a rectangle, then there is a simple closed curve that goes around it, right? There's the positive orientation of that curve. If you give me a type 1 region, there is a closed curve that goes around it, right? Like this. Give me a polar region. Right, that's a polar region. There is a curve that goes around it. This theorem somehow connects the line integral going around the region to the integral, the double integral over the area. Somehow they related to each other. And here's what it is. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane. So we're in two-dimensional space only. And let D be a region bounded by C. So Green's theorem is two-dimensional. There is a three-dimensional version of this theorem. It's coming. It's not this section, it's coming, all right? So we are going to get this in three-dimensional space, but right now we're working in two. So this theorem says that if P and Q have continuous partial derivatives, meaning we can just take the derivatives, then the line integral, this line integral, that should look familiar. This is the same as the integral over C of f dot dr. That's the same exact integral, written a different way. So the line integral along the curve C over the vector field, right? This work integral is equal to the double integral over the region D of the partial of Q with respect to x minus the partial of P with respect to y with respect to area. So you can do line integrals by doing double integrals instead. And it works the other way around. You can actually do double integrals by doing line integrals. And this can make life very, very nice. Also notice some notation here. See the little circle around the integral sign? See that little circle? That symbol indicates that you have positive orientation of a closed path C. So if you just put C down here without this circle, then C does not have to be closed. But if you draw that little circle around the integral, then it is a closed path. Further, if you just draw the circle, it's implied positive orientation. If you want to do the opposite direction, then you would add this little arrow. See a little arrow there? That arrow would indicate, I'm reversing the direction, and therefore it's negative orientation for the curve. clockwise. I'm going to write this down. Let's write it down right here. So we're going to go partial q respect to x minus partial p respect to y with respect to area. Okay, that's the Green's theorem right there. Let's see it in action. I think you can't appreciate this theorem until you see it in action. Okay, we're going to evaluate this line integral where C is the unit circle oriented, the unit circle centered at the origin. All right, so we are being asked to evaluate this along this circle C centered at the origin in oriented, positive orientation, right? Because there's just a little circle here. So we want to imagine that we're going to start at a point, we're going to move around this circle one time, and we're going to be moving through a vector field, and we're going to be trying to calculate the work, all right? Now, can anybody tell me what F is here? It's two-dimensional, right? PQ? Can you tell me what P and Q are? What is it? Don't confuse the curve. Don't confuse the vector function that draws the curve with the vector field.
Negative x.
So this is what? Look at right here.
What's her?
P dx plus Q dy, right? So what is P? Y, and what is Q? Negative x. Okay? That's our vector field. Now, what is R of t? That's what's going to draw the curve. That is the vector function cosine t sine t. And what is our restriction on t? 0 to 2 pi. By the way, is this a conservative vector field? We should have maybe checked that to begin with. Is this a conservative vector field? What is the partial of, what's the check you do? Partial of Q P with respect to Y, which would be 1, and then partial of Q with respect to X, which would be -1, and they're not equal. It's not conservative, right? So you cannot use the fundamental theorem of line integrals and say, what would the answer be? If this was conservative, what would the answer be? 0, because it's a closed curve, right? You're going to start and end at the same point, so the difference between the two endpoints would be 0. And then there would be no work, we'd be done. We move on, right? But since it's not conservative, we'd have to grind this thing out. We would have to go integral 0 to 2 pi, and then we're going to take the F vector field, and we're going to evaluate it at R of t, and then dot that with R prime of t dt. This is the formula for work. This is it. So this would be integral 0 to 2 pi. What is f of R of t? Means you take this and plug it into f. So you replace all your x's with this and all your y's with this. So what do you get? The vector sine t, negative cosine t, right? That's y, which is sine t, negative x, which is negative cosine t. I'm going to dot that with what? The derivative of r. If you have no idea where I'm getting this formula from, it's from last class, in the class before when we were doing work, okay? So I'm assuming you've done all the homework for that, so you've been working with it, you know? Derivative of r is negative sine t, cosine t, and then dt. So what happens when I dot those together? I get integral 0 to 2 pi you're going to get negative sine squared t minus cosine squared t. You can factor out the negative. It's going to be just negative 1. So this is going to be negative 1 dt. And what's the antiderivative of negative 1? Just negative t, evaluated 0, 2 pi. So the answer is negative 2 pi. Okay. I did not use Green's theorem there at all, did I? That was the good old-fashioned, I'm just going to do the line integral. There it is. But Green's theorem says that if you have a line integral, which is basically if you're trying to do this work, right? This right here. If you're trying to do that, then as long as that's a closed curve, then you can turn it into a double integral over the region D. Now D is this piece in here, right? That's D in there. And you're going to do the double integral of the partial of q with respect to x minus the partial p with respect to y with respect to area. Let's take a look at that. What does that look like? So I'm going to leave p and q up there. If I use Green's theorem instead, then I'm going to do the double integral over d. What is the partial of q with respect to x? Negative 1 plus, or minus, sorry, the partial of p with respect to y, which is 1 dA, like that. Agreed? Now let's see just how good you are. Let's see. This is really negative 2 double integral over d of 1 dA, right? Yes? You know what, Saba? Don't say it. I'm cutting you off. What is that? What's that? That's the area of what? Okay, so of what? Which is? What's the area of that circle? Which is? No, you know it. You're just trying to think too fast. Take your time. This means, this was the one I was going to whip everyone with the stick on, right? This means the area of D. All right? What is D? It's the unit circle. What's the area of the unit circle? Pi r squared. What's r? 1. What's the area of the unit circle? Pi, right? Pi. Yes? The area of that's pi. So if I come in here and there's no integration to be done. Negative 2 pi. Done. Same answer. You see that? This is going to happen several times from here on out, where we're going to get to this and we're going to be like, oh, well, that's just the area of the region we're integrating over. Do we know that area? Oh, we do. It's pi. Nothing to be done. Now, if you didn't do that, you would have to go and do a double integral over that region, which would require you convert it to polar coordinates, right? And it wouldn't be that bad. It would go from 0 to 1, 0 to 2 pi. We'd integrate, what would we integrate? R, because you did a polar conversion, right? R d theta. And you would get the same answer. But that's a lot more work, isn't it? So do you see how if you use Green's theorem in that problem, that you actually don't have to do any calculus at all, like no integration, nothing, no derivatives, nothing. Just you need to know the area of a unit circle. It won't always work out that way, but that I think shows some value in it. All right. Ooh, wow. Look at this one. Now this one is to make us truly appreciate Green's theorem. If that one didn't, this one will. All right. Let's identify P and Q. This is P, right? And this piece right here is Q. So if I did not know Green's theorem, then right now what I would need to